Good morning. Welcome to Unit 2 of Learning the course Design and Analysis of Algorithms. In this unit, we are going to learn about two algorithm design techniques, one divide and conquer method, two greedy method. The main objectives of this unit are learning the general method of divide and conquer strategy, applying divide and conquer in developing algorithms to solve various applications, learning the general method of greedy strategy, applying greedy strategy in developing algorithms to solve various applications, and analyzing those algorithms for their time and space complexities. The learning outcomes of this unit are, by listening this unit, one can understand divide and conquer and greedy algorithm design strategies and solve applications by developing algorithms by following those two algorithm design techniques and analyze the algorithms for their performance. Coming to the syllabus of this unit can be entirely covered in 10 sessions. In the first session, we are going to discuss about divide and conquer general method. In the second session, we are going to discuss about binary search, the first application of divide and conquer method. In the third session, we are going to discuss about merge sort. In the fourth session, we are going to discuss about quick sort. And in the fifth session, we are going to discuss about Strassen's matrix multiplication. Here, in the first session, we are going to see the general method of divide and conquer algorithm design strategy. From second session to fifth session, we are going to see various applications which can be solved by following the divide and conquer strategy. In the sixth session, we are going to see greedy method, general method. In the seventh session, we are going to explain about knapsack problem. In the eighth session, we are going to see job sequencing with deadlines. In the ninth session, we are going to see minimum cost spanning trees. In the 10th session, we are going to see tree vertex splitting problem. In the 6th session, we are going to see the general method of greedy algorithm design strategy. From 7th session to 10th session, we are going to discuss about various applications that are solved by following the algorithm design technique, which is nothing but greedy method. Various digital content that I used in this presentation are taken from different public sources. It is only used for educational purpose, not for any commercial purposes. Welcome to session 1 of Unit 2 in learning the course Design and Analysis of Algorithms. In this session, we are going to discuss about divide and conquer general method. The main objectives of this session are to learn the general method of divide and conquer algorithm design strategy. The learning outcomes of this session are, by listening this session, one can be able to understand the general method of divide and conquer strategy and able to follow divide and conquer strategy to develop algorithms for solving various applications. Now, the concepts that we are going to discuss in this session are the general method of divide and conquer strategy, control abstraction for divide and conquer strategy, time complexity of divide and conquer algorithms, and master's theorem. Now I am going to play a small video clip which gives the better understanding of divide and conquer general method. Let us see this video. I hope you understand that video clip. There they explained dividing the problem, getting the solutions of those sub-problems and combining the solutions. If you not understand, I will explain you here clearly what is divide and conquer general method. Let us see the general method of divide and conquer problem. We are given a problem. We are given a problem to solve. Here we are given a problem to solve. If this problem is a small problem, if this problem is a small problem, then we can go for finding the solution of that problem without dividing it. If the given problem is complex problem, in this case we are going to divide the problem into subproblems. Here I divided the problem into two subproblems. Then if the subproblems are small enough, then we go for finding the solutions of subproblems, and these solutions are combined to get the solution of given problem. But here, if these subproblems are also large enough, then these subproblems are again divided into subproblems. Again divided into subproblems. And if these subproblems are large enough, then these are divided into again subproblems. Again subproblems. Now here I got a subproblem which is a very smallest subproblem which can be solved without further splitting. So I found the solution for this subproblem, and here I obtain the solution for this subproblem. So here I find the solutions for all those subproblems, and the solutions are combined to get the solution of this subproblem. Here the solutions are combined to get the solution of this subproblem, and the solutions of these two subproblems are combined to get the solution of this subproblem, and finally these two solutions are combined to get the solution of given problem. To get the solution of given problem. I hope you all understood what is divide and conquer strategy. Here we are given a complex problem. For solving that complex problem, we are going to divide the problem into subproblems. Each subproblem is solved independently. We get the solutions of those subproblems. All those solutions are combined to get the solution of given complex problem. The divide and conquer strategy is applied to the subproblems also if the subproblems are large. So we continue this procedure till we get a smallest problem that can be solved without further splitting. Let us see the control abstraction for divide and conquer general method. Here you can see the control abstraction for divide and conquer general method. Divide and conquer of P. If small of P, then written S of P. Here S of P is nothing but solution of P. Here we have given a problem P. Here we have given a problem P. If small of P, given problem is a small problem, then we are returning the solution of that given problem. Else, if the given problem is not a small problem, then what we are doing? Divide P into smaller instances such as P1, P2, Pk. Here K should be greater than 1. That is more than one subproblem we are dividing. Here the P is divided into K subproblems. Those subproblems are nothing but P1, P2, so on Pk. Apply divide and conquer to each of these subproblems. Apply divide and conquer to each of these subproblems and return combine divide and conquer of P1, divide and conquer of P2, and so on divide and conquer of Pk. That is, here I applied divide and conquer technique for the subproblem P1, I applied divide and conquer technique for the subproblem P2, and so on. I apply divide and conquer technique for the subproblem Pk, and I get the solution of Pk, I get the solution of P2, I get the solution of P1, and all these solutions are combined to get the solution of P, which gives the control abstraction for divide and conquer strategy. So I hope you all understood the divide and conquer general method. What is the general method of divide and conquer? What we explained in control abstraction. The same, the general method itself is explained in control abstraction. Here we are given a complex problem. To solve that complex problem, we are going to divide the problem into some number of subproblems. Each subproblem is solved independently. We get the solutions of those subproblems. These solutions are combined or conquered to get the solution of given complex problem. Even after dividing, the subproblems are large. In that case, we are going to apply the divide and conquer method to those subproblems also. This process continues till we get a smallest subproblem which can be solved without further splitting. Let us see the time complexity of divide and conquer algorithms. Here, the time complexity of divide and conquer algorithms can be represented by using a recurrence relation. Let us see the recurrence relation. T of n is equal to T of 1 when n is equal to 1, and T of n is equal to A into T of n by B plus F of n when n is greater than 1. Here A and B are constants and T of 1 is also a constant. Here what about this recurrence relation? Here this is the recurrence relation which indicates the time complexity of divide and conquer algorithms. Now we are saying n. What is n? The input size of the given problem. Here n is input size of the given problem. If n is equal to 1, that is the given input size is a very small. Here we have given a smallest problem. In that case, we can directly return the solution of the problem. Without splitting that problem, we can solve that problem. So, the solution of that problem can be obtained within a small time. So, that's why its solution time or its time complexity can be represented as a constant, which is nothing but T of 1. When n is equal to 1, since the given problem is the smallest problem, we can solve that problem without further splitting. So, its time complexity can be represented as a constant, which is nothing but T of 1. Now, when n is greater than 1, that is input size is greater than 1. That is, here we have given a complex problem. In that case, we are going to divide the problem. So, in that case, the time complexity can be represented as A into T of n by B plus F of n. Here, what is that A, what is that B, and what is that F of n? Here, the constant B indicates where we are dividing the problem. At half place, we are dividing the problem, or at 1/3 place, we are dividing the problem, or at 1/4 place we are dividing the problem, or at 1/7 place we are dividing the problem. Where we are dividing the given problem. So that is indicated by the constant B. And A, how many subproblems that we are considering in further processing. Suppose for example in binary search, if you consider binary search, we are dividing the problem into two subproblems. Every time we are considering only one subproblem into consideration. In that case, A becomes 1. But if you consider merge sort, there also we are dividing the given problem into two subproblems. But in further processing, we are considering both the subproblems. So in that case, A becomes 2. So like that, how many subproblems that we are considering in further processing is represented with the constant A. Then what about F of n? Here, for dividing the problem and for combining the solutions, we need to have some time. Here, that A into T of n by B is the time complexity for solving the subproblems. But here first we divided to get the subproblems. After that, after solving the subproblems, we are combining the solutions. For dividing the problem into subproblems and for combining the solutions, we are spending some time. That time is represented by using the function f of n. Here, the time complexity of the recurrence relation for the time complexity of divide and conquer algorithms is represented by T of n is equal to T of 1 when n is equal to 1. and a into t of n by b plus f of n when n is greater than 1. Now, the time complexity obtained by solving the above recurrence relation is, that is, by solving this recurrence relation, we will get the time complexity as t of n is equal to, is identically equal to, here we call this as identically equal to. Never we represent the time complexity as directly equal to. We give the approximation values. So that's why we always represent it as identically equal to n log a base, n power log a base b, t of 1 plus u of n. Here this is n power b. T of n is identically equal to n power log a base b into t of 1 plus u of n. Here what I know what is a and what is b, what is t of 1. But here I don't know what is u of n. What is u of n here? The u of n can be obtained by this relation. Sigma j is equal to 1 to n h of b power j. Here u of n can be obtained with sigma j is equal to 1 to n h of b power j. What is this h of b power j? That can be found by this function. H of n is equal to f of n by n power log a base b. Here this is also n power log a base b. F of n by n power log a base b. So to simplify all this process, to get the time complexity of all the divide and conquer algorithms in a simplified way, I have represented the corresponding values of u of n for h of n here. Here, these are the values of u of n and these are the values of h of n. We are going to find h of n values. For the h of n values, the corresponding u of n values are represented here. Let us see. If h of n is big O of n power r, if h of, here we have to read this as big O, which is a notation used to represent time complexity. We will discuss about that notation in our further sessions. But here you have to remember this. This can be read as big O, big O, big O of n power r less than 0. If h of n is equal to big O of n power r less than 0, the corresponding u of n is big O of 1. If h of n value is big O of log n power I greater than or equal to 0, in that case the u of n becomes big O of log n power I plus 1 by I plus 1. If h of n is big O of n power r greater than 0 here r less than 0, here r greater than 0. For greater than 0, the corresponding value of u of n is big O of h of n. Now, by using these values, we can calculate the time complexity of any divide and conquer algorithm. Now, I am going to explain how to calculate the time complexity of any divide and conquer algorithm. Now, let us take an example here. T of n is equal to, I have given 5 when n is equal to 1, and here I have given 4 into T of n by 2 plus n when n is greater than 1. Suppose if you have given the recurrence relation as T of n is equal to 5 when n is equal to 1 and 4 T of n by 2 plus n when n is greater than 1. Now, how to solve this recurrence relation to obtain its time complexity? Let us see here. Now, first compare this relation with, compare this recurrence relation with general recurrence relation. General recurrence relation. By comparing this relation with general relation, we will get T of 1 is equal to 5, A is equal to 4, B is equal to 2 and F of n is equal to n. We get T of 1 is equal to 5, A is equal to 4, B is equal to 2, F of n is equal to n. Now, how to solve this recurrence relation? Now the time complexity T of n becomes n power log a base b into T of 1 plus u of n. T of 1 plus u of n. Now this is equal to n power log, what is a? Here a value is 4 and b value is 2. Log 4 base 2. Here T of 1 is 5 plus u of n. Here I don't know the value of u of n. I need to find the value of u of n here. Now how to find the value of u of n? For finding the value of u of n, you need to find the value of h of n first. Now how to find h of n? H of n is equal to f of n by n power log a base b, which is equal to, here f of n value is n by n power log, what is a? 4 base 2. Now how to simplify this? N by n power log 2 square base 2. Here I can write 4 as 2 square. Now this can be written as n by n power 2 log 2 base 2. That is, log 2 square can be written as 2 log 2. So that's why I have written 2 log 2 base 2. Here log 2 base 2 becomes 1. Hence we got n square. N by n square, which is equal to 1 by n, which can be represented as n power minus 1. Which can be represented as n power minus 1. Now here I am representing this as n power r less than 0. Since the r value is minus 1, I am writing that r is less than 0. Now in this case, what becomes the corresponding value of u of n? What becomes the corresponding value of u of n? Let us see the table what we have explained. N power r less than 0. In that case, u of n is big O of 1. So the u of n value becomes big O of 1. So u of n is equal to big O of 1. Now the time complexity T of n is equal to, in the same way here also we are simplifying. By simplifying it, we will get n square. Here also we can write log 2 square base 2. Log 2 square means 2 log 2. 2 log 2 base 2. Log 2 base 2 means 1. So we will get n square. N square 5 plus big O of 1. 5 plus big O of 1. Now T of n, here you need to write identical equal. T of n is identically equal to, since this 5 is constant, I am omitting that 5. Since it is constant, I am omitting that 5 and I am multiplying the n square with 1. We will get T of n is equal to big O of n square, which gives the time complexity of given recurrence relation. Now I am going to explain the next one, which is nothing but Master's theorem. So this is also used to find the time complexity of divide and conquer applications. What I explained earlier is the general method, substitutional method. Now here this is the Master's theorem. Both can be worked in the same way. Any method you can use to find the time complexity of a divide and conquer algorithm. You can follow the substitution method, what we discussed till now, and or you can follow the Master's theorem. Let us see the Master's theorem. Here the given recurrence relation is of the form T of n is equal to a T of n by b plus f of n. Here the function f of n is in the form n power k log n power p. Here a greater than or equal to 1, b greater than 1 and k greater than or equal to 0 and p is a real number. Now the time complexity of this recurrence relation can be calculated in 3 cases. Now what are those 3 cases? Let us see. The first case, if a greater than b power k, if a greater than b power k, then time complexity becomes big O of n power log a base b. If a greater than b power k, then T of n becomes big O of n power log A base B. Next, the second case, if A is equal to B power K, if A is equal to B power K, here we have three alternatives. In this case, we have three alternatives to find the time complexity. If P greater than minus 1, if A is equal to B power K, here we have three cases, three alternatives to find the time complexity. The first alternative is if P greater than minus 1, then T of n is equal to big O of n power log A base B log n power P plus 1. Big O of n power log A base B log n power P plus 1. Now, if P is equal to minus 1, then T of n is equal to big O of n power log A base B log of log n. N power log A base B log of log n. Now, if P less than minus 1, then T of n is big O of n power log A base B. Big O of n power log A base B. The third case is if A less than B power K. If A less than B power K. Here we have two alternatives to find the time complexity. The first one is if P greater than or equal to 0, then time complexity T of n is equal to big O of n power K log n power P. If P less than 0, then T of n is equal to big O of n power K. Now, by using Master's theorem, how to find the time complexity? Let us see an example for this. Now here I have given the recurrence relation. Here I have given the recurrence relation T of n is equal to 4T of n by 2 plus n. Here I taken the same example what we seen earlier. The same example I have taken. Now I want to find the time complexity of this recurrence relation. Now for finding the time complexity, first you need to compare this recurrence relation with general recurrence relation. Compare this recurrence relation with general recurrence relation. By comparing, we will get A value is 4, B value is 2 and f of n value is n. F of n value is n. But what about the representation of f of n? You can see earlier we have f of n as n power k log n power p. N power k log n power p. Now let us see how to write that f of n as n power k log n power p. N power 1, here I am writing into 1. It not changes the value of f of n. If I write n power 1 into 1, which becomes n, it does not changes the value of f of n. Now here I am writing n power 1 into log n power 0. That 1 I am replacing that 1 with log n power 0. That is log n power 0 is 1. So it not changes the value of f of n. So here k value is 1 and p value is 0. K value is 1 and p value is 0. Now we need to compare a and b power k. Here we have three cases. Those three cases are depending on the comparison of a and b power k. So I am taking those two values. Here a value is 4, b value is 2 and k value is 1. 4 and 2 power 1 which is equal to 2. Now what is the relation between these two? Here a is greater than b power k. Here a is greater than b power k. Since a value is 4, b power k value is 2, a is greater than b power k. Now in this case, what is the time complexity? If a is greater than b power k, then t of n value is big O of n power log a base b. So here the time complexity t of n is equal to big O of n power log a base b. Here a is 4, b is 2. By simplifying this, we will get n power log 2 square base 2, which is equal to big O of n power 2 log 2 base 2. So here the time complexity T of n can be represented as big of n square. What we obtained in the substitution method for the same recurrence relation, here also we obtain the same time complexity. So you can use the substitution, either substitution method or Master's theorem to find the time complexity of divide and conquer algorithms. Now I hope you all understood what is the general method of divide and conquer algorithm design strategy, and also you all understood, I hope you all understood how to find the time complexity of those algorithms. Now I am going to summarize the concepts what we explained in this session. In this session we explained about what is divide and conquer general method and what is the control abstraction for divide and conquer general method, and also we seen what is the recurrence relation that we use to find the time complexity of divide and conquer applications, and how to solve that recurrence relation to find the time complexity of various applications in substitution method, and also we see the Master's theorem which is used to find the time complexity of various divide and conquer applications. Now to assess yourself, here I given some questions. Let us answer these questions. In divide and conquer method, option A, the given problem is divided and solved. Option B, the given problem is divided and subproblems are solved, solutions are conquered. Option C, the given problem solved directly. Option D, it cannot be used to solve any problem. The next question is, solve the following recurrence relation. T of n is equal to 8 when n is equal to 1, and T of n is equal to 8 T of n by 2 plus n when n is greater than 1. Here, to solve this recurrence relation, use substitution method. You have to use substitution method. In substitution method, solve this recurrence relation. The next question is, solve the following recurrence relation using Master's theorem. Here the same recurrence relation I given, T of n is equal to 8 T of n by 2 plus n. Solve this recurrence relation by Master's theorem. Explain, the next question is, explain the general method of divide and conquer method with its control abstraction. So write answers for all these questions and share the answers through the given mail. Here various digital content used in this presentation collected from different public sources. This presentation is only used for education purpose and not for any commercial purposes. Thank you for listening the session.